Okay, so in the previous class, we discussed about non-degenerate semiconductors. And if you recall the definition of non-degenerate semiconductors, these are the semiconductors which have low doping level. Means if it is N-type semiconductor, then it will have smaller doping of the donors, and if it is P-type semiconductor, then it will have the lower doping of acceptor atoms. So I am saying that N and P type semiconductors will have smaller doping levels if they are the non-degenerate semiconductors. So now the question arises, this lower is with respect to what? So if the doping is smaller than the effective density of states for N-type semiconductor, it is effective density of states at the conduction band edge, and for the acceptor atoms, it is the effective density of states at the valence band edge. If you recall, I showed you one slide, this slide, in which the effective density of states at the conduction band edge and the valence band edge are given for different semiconductors. And these values, the order of these density of states are 10 to the power 19. It varies from 10 to the power 17 to 10 to the power 19 for different semiconductors. But you recall that it is of the order of 10 to the power 17 to 10 to the power 19. So if the doping level is like 10 to the power 14 per centimeter cube, 10 to the power 15 per centimeter cube, which is much smaller than these numbers, therefore such semiconductors will be called as non-degenerate semiconductors. They will not have any unusual properties. Their properties will be much like that of semiconductors. So for such semiconductors, the band gap at least lies 3 kBt above the valence band edge or 3 kBt below the conduction band edge. And because the energy difference is not too much, all the donors or acceptors can be completely ionized, and this process is known as complete ionization. If we have N-type semiconductor, that is a non-degenerate semiconductor, so at a particular temperature we can have the electron concentration in the conduction band that is given by the whole electrons are donated by the donor atoms. Similarly, in the valence band, we can have a situation where all the holes are donated by the acceptor atoms. So you can see from these two diagrams or pictures that at a particular temperature, these plus sign inside the circle, they represent the donor ions. So at particular temperature, each donor atom has contributed one electron to the conduction band. So you see that at this temperature, at this particular temperature, number of electrons per centimeter cube, that is electron concentration in the conduction band, is equal to the donor concentration. Similarly here, the whole concentration is equal to the acceptor concentration. So it is the process of complete ionization. And recall, this dashed line, it represents the Fermi level of intrinsic semiconductor. Intrinsic semiconductor means it has not been doped by donor or acceptor, and you see it is shown by a dashed line because in this region it is a forbidden region, not allowed region. So this means that no energy level would exist inside this forbidden gap. That's why it is not an actual energy level and it is shown by dashed line. So EI, so somewhere you will find that EFI is written. That represents the intrinsic Fermi level, but here we are using this notation EI. I here represents, or I stands for intrinsic energy level. So then we found the position of Fermi level in terms of the bottom of the conduction band. So EC minus EF is equal to KBT natural log Nc divided by Nd. Nc is effective density of states at the conduction band edge. Nd is the donor concentration. And similarly, we found a relation between the difference in the Fermi energy and the top of valence band. Ef minus Ev is equal to kBt natural log Nv over Na. So from these two expressions, we can see that if we increase Nd or Na, so this both are in the denominator, so this ratio will increase and natural log value will increase. So this value will increase means, so this means that Fermi level will move closer. When Nd and Na are increasing, so this ratio will decrease because Nd and Na are in the denominator. So this ratio will decrease. So natural log will decrease, and the difference between Ec and Ef will decrease. Similarly, the difference between Ef and Ev will decrease on increasing the acceptor concentration. So this means that the Fermi level will move closer to the conduction band for the N-type semiconductor, and it will move towards the valence band for P-type semiconductor. So on here, what is shown is that we have shown acceptor levels, and there are. It is basically N-type semiconductor in which you can see that number of electrons in the conduction band is more than the number of holes in the valence band. So these electrons are donated by these donor levels, and here the second diagram shows the density of states. So you see that the density of states for the valence band and conduction band, it varies, or it is proportional to square root of energy. That's why these are the parabolic graph. But here the donor concentration is very small. Donor concentration is very small. That's why they form the density. Their density of states is a very small band. Then we now have the idea of the density of states, how it varies with energy, and then we have this f of E, that is the probability of finding the electron at energy level E, or it is Fermi-Dirac distribution function. So you can see that since there are few number of electrons in the conduction band, that's why this is not zero. We have the finite probability of finding the electron in the conduction band. And since it is N-type semiconductor, so this area, which has been obtained by multiplying density of states with the Fermi-Dirac distribution function. So the area here represents the number of electrons per unit volume, or the electron concentration in the conduction band. And it is because it is N-type semiconductor, so the area in the conduction band is large. And similarly, following the mass action law, which is N into P is equal to Ni square, so the whole concentration would be very small, and the area enclosed by the curve would be much smaller in comparison to the area enclosed by this curve in the conduction band. All right. So is there any problem? Am I not audible? Somebody writes. Somebody asks. Am I audible? Can anybody tell me? Okay. So this means so many you are having some problem. So then we discussed about the variation of Fermi energy with respect to temperature and the donor or acceptor concentration. You see, when the you have the acceptor donor levels, and Fermi level lies for N-type semiconductor. The Fermi level lies between the donor levels and the acceptor level. And for p-type semiconductor, the Fermi level lies between the acceptor levels, which are not shown here, and the top of valence band. Now, if we increase the temperature, so donors and acceptors will start getting ionized. The Fermi level will move up. Fermi level will move up. Means it will acquire the value that for the intrinsic semiconductor. And you can see higher is the smaller is the doping concentration, lesser is the temperature required at which the n-type semiconductor will become intrinsic semiconductor, or a p-type semiconductor will become intrinsic semiconductor. When you see the doping level is very large, 10 to the power 18 per centimeter cube, so the Fermi level moves very slowly towards the intrinsic case, and you require very large temperature, probably 1000 Kelvin or so, in order to convert that n-type semiconductor into p-type semiconductor. Again, if we choose any particular temperature, for example, let's consider this 400 Kelvin, and we have different doping levels: 10 to the power 12, 10 to the power 14, 10 to the power 16, 10 to the power 18 per centimeter cube. And you can notice that we require more temperature to convert these semiconductors into intrinsic semiconductor. Now, we discuss about degenerate semiconductors. It is also one of the important class of semiconductors useful in many semiconductor devices. So when we keep on increasing the donor doping or acceptor doping, so what happens is that when the donor or acceptor concentration becomes equal to or larger than the corresponding effective density of states, means the donor doping or the acceptor doping is very close to 10 to the power 18 or 10 to the power 19 per centimeter cube. And we have seen that when we increase the doping level, Fermi level moves for n-type semiconductor, it moves towards the conduction band, and for acceptor level, it moves towards the valence band. Therefore, for such semiconductor in which we have the doping level equal to the effective density of states, such semiconductors are known as degenerate semiconductors. Degenerate semiconductors. An important aspect of high doping is the band gap reduces. Band gap gets reduced. There is reduction in the band gap on increasing the doping levels. So the reduction in band gap is given by this formula, delta Eg. It is the difference of the band gap previously before doping and the band gap after heavy doping. So delta Eg is equal to 20 under root or square root of n divided by 10 to the power 18, and it is in milli electron volt. N here represents either the donor concentration or the acceptor concentration. So, for example, if the donor concentration is less than equal to 10 to the power 18 per centimeter cube, it should have been per centimeter cube. It is not centimeter cube. It should have been per centimeter cube. So if it is equal to 10 to the power 18, you write here 10 to the power 18, 10 to the power 18, both will cancel. You will get 1 here, and it is 22 milli electron volt, that is 0.022 electron volt. If it is silicon semiconductor whose band gap is equal to 1.1 electron volt, so this change in band gap with 10 to the power 18 per centimeter cube doping is it is just the change in band gap is 2% of the original value of the band gap. However, if we have ND that is equal to 10 to the power 19 per centimeter cube, so in that case, the change in band gap would be significant. So we can, with this value, we can see that the change in band gap is equal to 0.12 electron volt, which is like in comparison to 1.1 electron volt, it is significant. So when we increase the doping level, the reduction in band gap is significant when it is comparable to the effective density of states. Is there any question? Any question you would like to ask so far? Okay, no question. So, how we have defined a degenerate semiconductor? A degenerate semiconductor is a semiconductor with very high level of doping, and the doping level is so high that the material starts to behave more or less like a metal, not as a semiconductor. For degenerate semiconductor, the resistivity is proportional to temperature, like that for metals. So these non-degenerate semiconductors do not obey the law of mass action, that is the product of electron and hole concentration is equal to Ni square. So these degenerate semiconductors do not follow the law of mass action. Now we try to understand what is happening when we keep on increasing the doping level. What is going to happen? So if the doping level is very small, if the doping level is very small, 10 to the power 12 per centimeter cube or 10 to the power 14 per centimeter cube, so dopants are lying here and there. They are very far away from each other because their concentration is very small. So their atoms or ions will not interact with each other, means their wave functions will not interact with each other. What they can do is they can just donate the electrons to the conduction band. But when the doping level is very high, when the doping concentration is very high, so we have large number of donors or acceptor atoms and they are very close to each other. So their wave functions will start overlapping and they will form a band which is known as impurity band, and this band will overlap for n-type semiconductor. It will overlap with the conduction band, and for p-type semiconductor it will overlap with the p-type semiconductor. So such degenerate semiconductor, it ceases to show the typical behavior of a semiconductor. If you recall, for a semiconductor, if we increase the temperature, its conductivity increases or resistivity decreases. But for degenerate semiconductor, I told you that conductivity becomes proportional to 1 upon T. Conductivity becomes proportional to 1 upon T. So such semiconductors behave more or less like metal, but they are not actually metal. So because the reason being, still the carrier concentration is much smaller in comparison to that of metals. Can anybody tell me what is the electron concentration in case of metals? What is the electron concentration in case of metals?
10 to the power 23 per centimeter cube.
Yes, 10 to the power 23 per centimeter cube. But here we are having 10 to the power 18 to 10 to the power 19 per centimeter cube, which is much smaller than this 10 to the power 23. So still it behaves like a metal, but it is not actually a metal. So its behavior is intermediate between semiconductor and metals. But because its resistivity becomes proportional to temperature, that's why we say it behaves like a metal. But the electron concentration or the carrier concentration in degenerate semiconductor is far smaller than that in case of metals. So these semiconductors, which are degenerate semiconductors, they are used in integrated circuits to make contact between different components, and So if we have a degenerate semiconductor, we will denote it by a plus sign in the superscript. If it is n-type degenerate semiconductor, so you will find a plus sign here. So by looking at this symbol, you will identify that it is n-type degenerate semiconductor. If it is not so, if it is a non-degenerate semiconductor, you can find either there will not be any superscript or you will find a minus sign. That means it is lightly doped. It is lightly doped, P minus. Another very important application for the degenerate semiconductor is to make Izaki diode or the tunnel diode. So Izaki was the Japanese scientist who fabricated this tunnel diode. So it is known as by the name Izaki diode or tunnel diode. It is a very heavily doped diode in which the Fermi level lies inside the valence band, and for n-type semiconductor, the Fermi level lies inside the conduction band. So this is have n-type degenerate semiconductor, and B part of the graph it is p-type degenerate semiconductor. These are the semiconductors used to fabricate tunnel diode, and we have discussed that when we fabricate any device under thermal equilibrium, there should be one Fermi function. So for n-type semiconductor, the Fermi level is here. For p-type semiconductor, the Fermi level is here. But when we join them, there will be one Fermi level. So inside, you see that in between the bottom of conduction band and the Fermi level is shown by EFN. It is the Fermi level of n-type semiconductor. We have large number of electrons. So for p-type degenerate semiconductors, we have large number of holes or the empty states between EFP and the top of valence band. So when we join them, there will be one Fermi function. These empty states will be in front of these electronic states, and these electrons can tunnel from n side to p side, leading to the flow of current. Do you have you ever seen the behavior IV characteristic of a tunnel diode? Have you ever seen? Anybody else?
Yes, yes, yes.
So what kind of IV behavior it is?
Actually, I'm exactly not remembering, but this is like a hill, like etc. So first increases and then approaches a peak, then decreases, something like that.
Yes, the famous property of a tunnel diode IV characteristic is that it shows negative resistance region. It shows negative resistance region means with increasing temperature, with increasing voltage, the bias voltage, the current decreases in a particular region. So you must remember it is interview question. You may be asked that tell the name of a device, semiconductor device, because now you have opted for this course, elective course. So you may be asked, tell the name of a semiconductor device which shows the negative resistance behavior. So it is tunnel diode, in which the IV characteristic exhibits the negative resistance. It is known as negative resistance. Or somewhere you may be asked that there is positive resistance, superconductors in which when the material becomes superconductor, you have zero resistance. Do you know any material or any device where you get negative resistance? So then you can tell that it is tunnel diode where you get negative resistance. All right. So now after discussing the degenerate semiconductors, now we move to discuss the direct and indirect band semiconductors. If you recall, in the previous class, we discussed several semiconductors in which we wrote symbol like like I or D. So, for example, germanium is I, silicon is I, gallium arsenide is D. So, D here represents direct band semiconductor, and I here represents the indirect band semiconductor. So, now we discuss what do we mean by direct and indirect band semiconductors. So, this is a particular EK diagram for a semiconductor. And for free electron, it should have been a perfect parabola. But as we study in the condensed matter physics course, that electron in semiconductor is not as much free as we think. So its behavior, the EK diagram is not completely parabola. It deviates from the parabola, and you see the curvature. You see the curvature. How it is here. It is upward, and here it is downward. So the behavior of electron, which is present at the bottom of conduction band, is completely different from the electron that is present here at the top of conduction band. So because here curvature is upward, here curvature is downward, so here the effective mass is positive, and at the top the effective mass is negative. The effective mass is negative, and it is very close to the boundary of Billuma zone. It is very close to the boundary of Billuma zone. So here the electron behaves differently in comparison to the electrons here. All right. And similarly, we have the EK diagram for the valence band, in which these circles, they represent the field states. Blue circles represent the field states. Now somehow we excite some of the electrons, or we break the, if it is if it is a, for example, gallium arsenide semiconductor, we break some covalent bonds. So then the electrons would be released, and they would be easily available for conduction. Means we have shifted the electrons from the valence band to the conduction band. Now these electrons which are present here, they will not remain there forever, because these are the excited states. They will fall or they will again come into the covalent bond when the electron hole pair recombines. The difference of energy is equal to band gap, because these electrons are exactly located at the bottom of conduction band, and these holes are at the top of valence band. So their difference in energy is exactly equal to the band gap. So this difference is emitted in the form of a photon. You see the symbol of photon. It is not very sharp, it is rounded here. For phonon, it is very sharp. These edges are sharp for phonon, and for photon, it is round in shape. So you see, this is the symbol. So the emitted photon will have the energy h nu that will be equal to the band gap. So this type of method is also used to calculate the band gap of semiconductors. It is also used. So if we shine light which is equal to the band gap of this semiconductor, then we can promote the electrons from the valence band to the conduction band. We can promote the electrons. So because that photon will be absorbed here. So means the energy of that photon will be equal to the band gap of semiconductor. So this thing is used to calculate the band gap of semiconductors. The same thing is shown here. The blue rectangle, it shows, or it represents the valence band, and the yellow rectangle, it represents the conduction band. And somehow there are two holes in the valence band and two electrons in the conduction band. When the electron jumps from the conduction band to the valence band, the difference of the energy is emitted in the form of a photon. Now, if we want to use such semiconductors for light emitting purpose in the visible radiation, then the band gap of this semiconductor should be such that the corresponding wavelength of the emitted photon should lies in the visible region. Then we can use these semiconductors, such semiconductors for making light emitting diodes. This is the concept behind the fabrication of light emitting diodes. Now, what is shown here is these all blue circles here. These are they represent the electrons in the covalent bonds. So they represent their wave function is represented by the psi k x, where k is the corresponding wave vector, and in this region, because it is forbidden region, so no allowed solution exists for which is corresponding to psi kx in this forbidden region. Now, if we have the EK diagram for any particular semiconductor in which the top of valence band and the bottom of conduction band, they lie at the same K value. From figure A, you can see that top of valence band and the bottom of conduction band, they lie at the same K value. On the x-axis, we have K, and on the y-axis, we have energy. So K here represents the momentum or wave vector. So if such is the situation in which the top of valence band coincides with the bottom of conduction band, then such semiconductors are known as direct band semiconductors. Very important concept, you must remember it. And whenever in such cases the electron and hole recombination will take place, the energy would be emitted in the form of a photon. Photon, what is a photon? Photon is quantum of light. So light will be emitted in such cases when the top of valence band coincides with the bottom of conduction band. So we have seen that gallium arsenide is a direct band semiconductor. Silicon and germanium are not direct band semiconductors. So that's why gallium arsenide is the base material that is used to make the light emitting diodes. You must remember it. What is the material for making light emitting diodes? So it is gallium arsenide. So for gallium arsenide, band gap is 1.42 electron volt. Tomorrow you will tell me if the band gap is 1.42 electron volt, what would be the corresponding wavelength of the emitted photon corresponding to this 1.42 electron volt. So then in order to make different color LED, we dope either like phosphorus or aluminium in gallium arsenide, and we tune the band gap depending upon the requirement. So we can have the red color LED, we can have the green color LED, we can have the yellow color LED, and blue color LED was difficult to make, but scientists fabricated the blue color LED as well, and for that they were awarded the Nobel Prize in 2014. You can read more about this on internet. So now we have the three primary colors, red, green, and blue, and by combining these colors, we can have the LED of any color. We can have the LED of any color. So then, if the situation is such that for example, for silicon, the top of valence band and the bottom of conduction band, they are not at the same K value. The K value for the top of valence band is denoted by KVP, and the bottom of conduction band is denoted by KCP. So there is a large difference. There is a large difference in these two values. And for when such is the situation, these materials are known as the indirect band semiconductors. And here electrons cannot obliquely इलेक्ट्रॉन यहाँ से यहाँ डायरेक्ट नहीं आ सकता है. Oblique transitions are not allowed. Only vertical transitions are allowed. So this electron cannot directly come from here to here. That's why we will not have the generation of photons here, and this process will not lead to the generation of photons, but there is a third entity required which will take care of this difference in momentum. So generally this process of electron hole recombination takes place via a third entity. If any impurity level is there inside the forbidden region or inside the band gap, so first the this electron will come from here to here with the generation of phonon, and then this electron will jump from this impurity level to this hole, and again phonons will be emitted. And what are phonons? Phonons are lattice vibrations. So this difference of energy will be used to generate heat, not light. So this is the reason why indirect band semiconductors cannot be used for making LED, because we don't have the generation of large number of photons. In case of indirect band semiconductors, most of the energy difference is used in heating the semiconductor. Now, because this indirect band semiconductor, it involves three entity. One is electron, other is impurity level, and the third one is the hole. It involves three entity. And if you recall from the chemistry practicals, that a reaction that is involving two species is much faster than the reaction which involves three chemicals, let's say. So the direct band process is much faster in comparison to indirect band. So the time in the electron hole recombination for the direct band semiconductor is 10 to the power minus 8 to 10 to the power minus 10 second, whereas it is much slower than for indirect band semiconductor. The electron hole recombination is much slower. It is 10 to the power minus 2 to 10 to the power minus 4 second. So why a third entity is required? Because whenever the electron hole recombination has to take place, the conservation laws for energy and momentum must be satisfied. Now the question for you is that why a phonon is getting emitted here, not a phonon. So tomorrow you will tell me why in indirect band semiconductors we have the generation of phonon, not photon. Though there are some photons emitted, of course, when the electron jumps from here to here, sometimes a photon will be emitted, but the number of photons is very less in comparison to those emitted in the direct band semiconductors. Now there is a term we define, quantum efficiency. So quantum efficiency is a measure of how well a semiconductor material is in converting carriers into photons. So how good a semiconductor is in converting carriers into photons, because here electron hole recombination is taking place. There are two carriers involved. When they annihilate, the difference of energy is emitted in the in terms of photon. So we define a quantity that is known as quantum efficiency. So it is a measure of how good a semiconductor is in converting carriers into photons. Also it is the ratio of number of photons produced by the number of carriers crossing the junction between P and N. For indirect band semiconductor, the quantum efficiency is very, very poor. Very, very poor. So the example of direct band semiconductor, one is the gallium arsenide, it is direct band semiconductor. Indium arsenide, it is direct band semiconductor. Indium antimonide, INSB, it is also direct band semiconductor. Gallium nitride is also direct band semiconductor. Indium nitride is also direct band semiconductor. Zinc oxide is also direct band semiconductor. Cadmium sulfide, cadmium selenide is also direct band semiconductor. Zinc sulfide is also direct band semiconductor. And they have the different band gaps. So I think with this I should stop. Next time we will start a new topic. If you have any question, you please ask.
Sir, in the third figure, there are arrows, zigzag arrows with such phonons. Sir,
There
the
are
black zigzag arrow, sir, is it also a phonon?
phonon. Yes, it is also a phonon. Black one. And the question for you is why there should be a phonon, not photon in the indirect band semiconductor.
Okay, sir.
That is one question. And you please, I have asked you that you tell me for gallium arsenide the band gap is 1.42 electron volt. If we convert it into wavelength, what should be the wavelength? That is question number one. Question number two is why there should be phonon, not photon in case of indirect band semiconductor. Okay.
Sir, the wavelength is 8714 angstrom.
Yes, 8174 angstrom. 817.
8714, sir.
Yes. So, in which region of the electromagnetic radiation this wavelength lies?
Sorry, sir, I don't remember.
So tomorrow you tell. Okay. And the third question is that if you are given a semiconductor that is unknown, okay, means you are told that it may be a direct band semiconductor, it may be an indirect band semiconductor. By what method you will identify that it is a direct band semiconductor or indirect band semiconductor? So three questions to you. To you means all of you.